Nestled in the picturesque city of Geneva, Switzerland, the European Organization for Nuclear Research, commonly known as CERN, stands as a beacon of scientific exploration and discovery. At the heart of CERN's mission lies the quest to understand the fundamental constituents of matter, from the tiniest particles to the vast cosmic expanse. One of the most extraordinary scientific projects here is centered on the captivating tale of the antimatter factory, where visionary thinkers are stretching the boundaries of human understanding and technological prowess. Antimatter, as we know, is at the heart of a mystery about why the universe exists at all, so studying antimatter is also key to understanding our very existence. But in a quest to unravel one of the biggest cosmic mysteries, CERN has found something weird happened with antimatter that no one can explain. This finding then leaves a hanging puzzle that scratches scientists' heads. So what did exactly they find alarming? Join us as we dig deeper into CERN's new discovery that has the scientific community baffled. Antimatter sounds like science fiction, material that looks like ordinary matter but would unleash as much energy as an atomic bomb if even a speck of it came into contact with anything around us. Small wonder that the scientist who first predicted the existence of antimatter felt uneasy about what he had found. Nowadays, physicists are using gigantic particle detectors to probe subtle effects that they hope will explain the central mystery of antimatter. Where has it all gone? It is a question whose solution lies in the very first moments of the Big Bang almost 14 billion years ago. Something happened back then to turn a universe born with as much antimatter as ordinary matter into one strangely devoid of the stuff. Did the antimatter vanish as the result of some strange quirk in the laws of nature, or is it still out there somewhere, making up antiatoms in orbit around anti-stars? One thing is certain, despite its weirdness and rarity, antimatter is for real. The first hints of antimatter's existence emerged in 1928 when 26-year-old British physicist Paul Dirac announced his discovery of a single equation unifying no fewer than three of the key theories of physics: quantum theory, electromagnetism, and Einstein's special theory of relativity. In 1928, Paul Dirac made his astounding claim, making antimatter the focus of unprecedented attention. It was a spectacular achievement and one that won Dirac a Nobel Prize, but its implications were perplexing. Like quadratic equations familiar from school math, Dirac's equation had not one but two solutions. One of them made perfect sense and described the properties of that most familiar of particles, the electron, but the other solution seemed to describe another subatomic particle whose properties were the exact mirror image of the electron, with the same mass but opposite electrical charge, an anti-electron. What worried Dirac was that no one had ever seen such a particle or anything like it. Even so, he decided to put his trust in his equation and regard the new particle as a prediction. Dirac's faith was quickly rewarded. In 1932, physicist Carl Anderson at the California Institute of Technology had developed a new type of particle detector to study cosmic rays, incredibly fast particles hurtling through the atmosphere from deep space. A photograph taken with the detector revealed something utterly bizarre, the trace of a particle behaving as if it were the exact mirror image of an electron. It was the first sighting of the particle predicted by Dirac's equation for years earlier. Identical in mass to the electron but with a positive charge, it was duly dubbed the positron. But the discovery only served to highlight the mystery of antimatter. While electrons are ubiquitous, it took a state-of-the-art particle detector to find even a single positron. There was nothing in Dirac's equation or in the known laws of physics to explain why the universe should prefer matter to antimatter. So where was it all? One suggestion was that the Earth just happened to lie in a relatively antimatter-free region of the universe. Perhaps there were whole stars made out of the stuff lurking out there. If so, it would be easy enough to tell, for as soon as antimatter comes into contact with ordinary matter, it is totally destroyed in a huge burst of radiation. Einstein's famous equation, E=mc², shows that if just a single gram of antimatter comes into contact with ordinary matter, the energy released is equivalent to the detonation of an atomic bomb. In fact, matter-antimatter annihilation is the most potent source of energy in the universe, and its effects are hard to miss. So if there really are anti-stars or even whole anti-galaxies beyond our own, the Earth should be bathed in a constant glow of gamma radiation, the telltale sign of matter-antimatter annihilation. The reality could hardly be more different. Since the early 1960s, astrophysicists have sent ever more sophisticated gamma-ray detectors above the protective blanket of the atmosphere to see what is out there, and the message has been consistent: there are no signs of antimatter objects anywhere in the universe. The lack of gamma rays from our own galaxy suggests that the nearest anti-star must be at least 10 light-years away, with no more than one star in 10,000 being made from antimatter. On a larger scale, the absence of antimatter is even more striking. The level of gamma rays coming from distant galaxies suggests that no more than 1 part in 100,000 of extragalactic matter can be in the form of antimatter. But why is there more matter than antimatter? Did something happen during the Big Bang to get rid of antimatter while leaving enough ordinary matter behind to create the galaxies, stars, and us? The first hints of what that something might be emerged in 1964 when American physicists studying so-called CERN particles discovered a bizarre effect called charge parity, or CP, violation. This meant that antimatter does not always perfectly mirror the properties of ordinary matter. The level of CP violation detected was very small, but in 1967, the brilliant Soviet physicist and dissident Andrei Sakharov showed that it might just be enough to explain the matter-antimatter asymmetry. Explain why matter created in the Big Bang did not pair off exactly with all the antimatter, but two big question marks hung over Sakharov's suggestion. Firstly, to stand any chance of explaining the mystery of antimatter, CP violation had to apply to more than just K mesons. Second, even if it applied to all particles, the effect had to be strong enough to explain the huge preponderance of matter over antimatter that we see today. Physicists are now probing both these questions in gigantic machines that attempt to recreate conditions in the early universe. At Stanford University, California, the 1,200-ton BA-bar particle detector is being used to study the effects of smashing together electrons and positrons with a violence not seen since moments after the Big Bang. The collisions produce unstable particles called B mesons and their antimatter counterparts, whose decay can be studied for signs of CP violation. In 2001, scientists working at BA-bar and also at Bell, a similar experiment based in Japan, announced that they had succeeded in detecting CP violation among B mesons and their antiparticles, thus showing that the effect is not confined to one type of particle. Better still, the level of CP violation was right in line with theoretical calculations based on the so-called Standard Model, the best theory currently available for understanding subatomic particles. The bad news was that the measured level was far below that needed to explain the observed preponderance of matter over antimatter in our universe. Physicists are taking this as a sign that the Standard Model is lacking something crucial. Precisely what it might be remains unclear, but experiments are already being planned to find out. Astrophysics and particle physics are often dismissed as being utterly irrelevant to everyday life, but by attempting to explain how antimatter lost out to ordinary matter in the birth of the cosmos, they hold the key to understanding our very existence. That's also why physicists at CERN are searching for subtle ways that antimatter differs from matter. Indirect measurements of the effect of gravity on antimatter suggest that matter and antimatter both respond in the same way to gravity. However, the difficulties of working with antimatter meant that a direct observation of antimatter falling freely under Earth's gravity had not been made. While antimatter can be made in the lab, it will annihilate upon contact with matter in an experimental apparatus, so great care must be taken to accumulate enough antimatter to do an experiment. For the last 20 years, scientists from the Alpha Group have been collecting antimatter at CERN, siphoning high-energy antiprotons from collisions in the CERN proton synchrotron and slowing them from the speed of light to speeds of a few hundred feet per second and a temperature of about 15 degrees above absolute zero. The antiprotons are then mixed with a cloud of anti-electrons or positrons produced by the decay of radioactive sodium in a so-called mixing trap controlled by electrical fields. Normal hydrogen, the simplest and most abundant element in the universe, consists of a positively charged proton attended by a negatively charged electron. The alpha experiment results in a few atoms of antihydrogen, the nucleus is an antiproton, and a positron circles it. In 2002, Dr. Hansch reported that these antihydrogen atoms emitted and absorbed light at the same frequencies and wavelengths as regular hydrogen, just as Einstein would have predicted. Since then, many experiments, all indirect, have strongly suggested that antimatter also gravitates normally. But those experiments have not been conclusive because gravity is less than 1/trillionth as strong as the electromagnetic fields used to manipulate the antiatoms. In the latest experiment, the anti-hydrogen atoms were confined by a magnetic field inside a 10-inch-long metal container. Since, like hydrogen, anti-hydrogen atoms carry a slight magnetic field of their own, they bounce off the walls of this bottle. The magnetic fields can also be tuned to counter gravity and suspend the anti-hydrogen atoms in the bottle. In the experiment, when the fields were slowly ramped down, the atoms eventually escaped the field and annihilated themselves in a flash on the walls of the chamber. About 80% of these flashes occurred below the chamber. According to statistical analyses, this suggests that gravity typically acts to pull antiatoms downward just as it would with normal matter. Any violation of the expected symmetry between hydrogen and antihydrogen would have rocked physics to its core. However, that did not happen. In the words of Dr. Jonathan Wurtel, a physicist at the University of California, this experiment is the first time that a direct measurement of the force of gravity on neutral antimatter has been made. It's another step in developing the field of neutral antimatter science, but the result leaves hanging another puzzle. According to relativity and quantum mechanics, the two quarreling theories that rule the universe, the Big Bang should have created equal amounts of matter and antimatter, which should have annihilated each other long ago. But our universe is all matter, with nary a speck of antimatter to be found outside of cosmic ray showers and particle collider collisions. So what happened? Why does the cosmos contain something rather than nothing? The question has burned for almost a century already. 4 years ago, an experiment in Japan involving the strange particles known as neutrinos reported what might be a clue to the cosmic imbalance. At the Large Hadron Collider, an entire instrument called LHCb is devoted to searching for any differences between matter and antimatter that could have tipped the cosmic balance. Asked whether the results from the ALPHA experiment offered any insights for the LHCb team, Dr. Wurtel said, "Since our answer is consistent with normal gravity, I don't think it gives any hints, unfortunately, which is another way of saying we still don't know why we're here." While antimatter still is a puzzle, some interesting ideas come to mind. We all know that the birth of the universe in the Big Bang 13.8 billion years ago was marked by a period of extremely rapid expansion and the creation of both matter and antimatter particles in equal amounts. Matter and antimatter particles undergo mutual annihilation, releasing vast amounts of gamma rays. Radiation from perfect annihilation is blocked by a combination of the expansion of the universe and the effect of CP violation, ensuring more matter survives than antimatter. Radiation leaves a fingerprint in the number of photons to particles in the cosmos as seen in the cosmic microwave background, suggesting matter and antimatter annihilated each other to within 1 part per billion. Around 9 billion years after the annihilation process ends, around 10 to the power of 57 particles of matter come together under gravity to form the solar system. So what if the universe were made up entirely of antimatter? To answer this, we must first recognize that every subatomic particle has an antiparticle with opposite properties. The antiparticle of the negatively charged electron, for example, is the positively charged positron. Antiparticles can combine to make antiatoms and ultimately antimatter. Crucially though, the photon, the particle of light, is its own antiparticle. Consequently, if the universe were made of antimatter, it would look no different. So how do we know the stars are not anti-stars and the galaxies are not anti-galaxies? Well, when particles of matter and antimatter meet, they annihilate each other, their mass energy flashes into high-energy light or gamma rays. We know there are no anti-stars in our galaxy or anti-galaxies in the local group because matter mingles within these systems, yet we see no annihilation radiation. It looks as if we live in a universe of matter. This is a mystery because particles and their antiparticles are always created together. So why does the universe not contain a 50-50ths mix of matter and antimatter? A clue comes from the fact that there are about 30 billion photons for every particle of matter. This can be explained if, in the Big Bang, 30 billion and 1 particles of matter were created for every 30 billion particles of antimatter. After annihilation, there would be no antiparticles and 1 particle for every 30 billion photons. So, is there a fundamental asymmetry in the laws of physics that slightly favors the production of matter over antimatter? Remarkably, yes, and its name is CP violation. Currently, experiments are underway to see whether the asymmetry is big enough to account for our matter-dominated universe. In action, the universe made of antimatter, as told, would look no different from our current universe. So what if there were an antimatter black hole? Would there be anything different about it? Well, in fact, according to Einstein's general relativity, black holes don't particularly care what they are made out of. If you put a sufficient amount of mass together in a small enough volume of space, the gravitational pull within that region will prevent anything below a certain speed from escaping. Dial up the amount of mass and it becomes harder and harder to escape. You'll have to move even faster in order to do so. And for better or worse, there's a limit to how quickly anything can move within our universe, the speed of light in a vacuum. Whenever the speed needed to escape a region's gravitational pull is greater than the speed of light, that's the necessary condition for creating a black hole. In fact, the event horizon is defined by the border from where you can versus where you can't escape. In one of the more famous theorems in general relativity, there are only a few types of properties that a black hole can remember. They include mass, electric charge, angular momentum, and if it were to exist, magnetic charge. These properties are known as the types of hair a black hole can have. Although the shape and specific properties of a black hole's interior are defined by the values of these types of hair, there's no distinction between whatever other properties went into the composition of a black hole. In other words, if you had a black hole that was made out of 100% neutrons versus an otherwise identical one that was made out of 100% antineutrons, those two black holes would each have the same mass, the same charge, and the same angular momentum as one another. We know from both a tremendous variety of particle physics experiments and also a variety of provable theorems, such as the Kapteyn theorem, that every fundamental and composite particle that's made out of matter has an antimatter counterpart of equal mass, equal and opposite angular momentum, and equal and opposite electric charge. However, it's also true that if you collide a matter particle with its antimatter counterpart, they annihilate away back to pure energy via Einstein's E equals mc squared, with the mass of the matter particle and the antimatter antiparticle both being equal. Therefore, you might think that colliding a matter-composed black hole with an antimatter-composed black hole would cause the two to annihilate away, releasing a tremendous amount of energy in the process. But this shouldn't be the case. Once you create a black hole, it no longer remembers, at least in general relativity, what it was that it was made out of. We fully expect that black holes, like anything with mass, will gravitate according to the laws and rules set forth by our theory of gravitation, general relativity. Since antimatter and matter have equal amounts of mass, that means a black hole made out of antimatter, when paired with a black hole made out of matter, should orbit, emit gravitational waves, in spiral, and eventually merge in the same exact fashion that two black holes made of normal matter should. An antimatter black hole should have the same size and shape event horizon, the same rest mass, the same gravitational influence on the surrounding matter and antimatter, the same emission of gravitational waves, the same in-spiral and merger period, the same precessions, the same angular momenta, the same post-merger kicks, and even the same spectrum and rates of Hawking radiation as a normal matter black hole is expected to have. When they do merge with another, whether matter or antimatter, the same proportion of mass, about 10% of the lower mass object in the merger, should get emitted in the form of gravitational radiation. But with that said, general relativity isn't everything. There are also quantum rules that govern the universe, and some of those rules show stark differences between different types of matter. If you make a black hole out of a solar mass's worth of protons and electrons, a solar mass's worth of neutrons, a solar mass's worth of positrons and antiprotons, or a solar mass's worth of antineutrons, these black holes should not be the same. From the viewpoint of general relativity, they would be considered identical. They have the same mass, one solar mass, the same electric and magnetic charge, a net of zero, and identical spins and angular momenta, dependent only on their formation history. But from a quantum viewpoint, they ought to be different. Each one of these would have a different combination of baryon number and lepton number, which are conserved in every particle interaction we've ever witnessed. If we understand the quantum physics of black holes correctly, the debatable prospect, the information from the particles the black hole is made of is somehow encoded on the event horizon of the black hole itself. This is an example of the black hole information paradox. The entropy of the universe must never decrease, so this information must be preserved rather than destroyed. This implies a quantum memory that persists, imprinted onto the black hole itself, with the event horizon being the natural place for that encoding. If your black hole is made of antimatter, some property on its event horizon should remember the quantum properties of each particle that went into making this black hole. Each particle that crosses over from outside to inside the event horizon from the perspective of an external observer has its last moments smeared out over the surface of the black hole. When radiation is emitted from the black hole, whether electromagnetic Hawking radiation from decay or gravitational radiation from merging with another large mass, the information that went into the black hole should be preserved. However, these differences are very subtle and beyond our current ability to detect or predict how we would observe them. This realm of physics, where theoretical work is still being done, remains poorly understood. Observable, measurable signatures have not been extracted yet, and the properties of the gravitational waves emitted from an inspiral and merger, a phenomenon intrinsic to general relativity, may not have any quantum signature that we would recognize as information imprinted on them. This is one of the big open questions in all of physics. Is there a fundamentally quantum theory of gravity, and if so, how does its behavior differ from our classical theory of gravity, general relativity? These are the types of questions we'd have to answer to see a difference between two merging matter-based black holes versus a merging matter-based and antimatter-based black hole. There could be different polarizations encoded in the radiation, and if we can break that radiation down into individual quanta, discrete gravitons for gravitational waves, just like light waves can be broken down into discrete photons, we might discover different properties like spin values and their correlations, as well as potentially additional quantum numbers. This implies that, at least gravitationally, antimatter functions as a source of not just negative mass but also negative energy, making warp drive via the Alcubierre drive a realistic physical possibility. As far as what we expect, we have every reason to believe that antimatter gravitates just as regular matter does, rather than exhibiting antigravitational behavior. Would there be differences between an antimatter black hole and a matter-based black hole? At its heart, physics is an experimental science, so until we get definitive results, we'd be unwise to discount anything that experiment hasn't already ruled out. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.